Okay, so it's been a while since I've done one of these, but we're going to try what to do. We're going to try out problem 15 right here. This is lattice paths. So, problem gives you the example of a 2 by 2 grid. It tells you can only move right and down, and it tells you there's 6 routes through, and it shows you what these 6 routes are. So obviously at each stage you have the option of going right or down, and it's just basically find out how many of these different combinations there are. And it then wants you to expand this 2 by 2 to a 20 by 20, come up with an answer. So if you know anything about the branch of mathematics called combinatorics, you'll know this is 40 choose 20. And I spotted that, I then got the answer. So you can see here, if you type in Google 40 choose 20, get, where's that? Staying, whatever. So you see you get this answer right here, which is obviously the same. So I'm going to try this episode to program it using recursion. Since I've never actually programmed this problem before, I simply got the answer through 40 choose 20. So this episode is going to be quite long because I'm going to teach recursion as if you know nothing about it at all. It's quite powerful and really quite interesting. I was quite impressed by it when I first learned it. So yeah, this video might be quite long, but if you're interested in learning about recursion, then this is probably for you. So what we're going to do, I'm expecting recursion to take a long time processing wise, so probably not going to be able to solve the 20 by 20, but I'm going to look at solving smaller grids, and then eventually it would solve a 20 by 20. It's just going to take a lot of time. We'll see. So we're going to use the fact that we can do 40 choose 20. We're going to do something like 20 choose 10, and we're probably going to look for like this answer. We're probably going to make like the smaller grid, so it's like a 10 by 10 grid we're solving, but it'll be like the same idea, so we'll know we've done it. So yeah, that's the plan, so let's get into it. So what we're going to do first is I'm actually going to take the Fibonacci sequence that we did in problem 2, and we're going to code the Fibonacci sequence as a recursive problem. So if I take this right here, and I say we want like 1,000. What's going on? So the 1,000th Fibonacci number is that? I can't remember what this is finding. Oh, this was finding like the sum of something. So if I delete some of this, don't need this. Total. Sequence starts 1, 2. Fib next equal. So the sequence actually starts 0, 1. I don't know why it 1, 2. But yeah, see, it actually starts 0, 1, and then the next one equals 1, then 2, and so on and so on. So I'll just change that. So what this does is it takes the last element, adds it to the second last element, and then returns that as the next element. So if I print out, if I go up to 100 here, and I print out fib sequence, we should see, yeah, so we see a list of all the Fibonacci numbers up to 100. So we get 0, 1, 1, 2, 3, 5, so on and so on. So what I'm aiming to do is print out this list using recursion. So in recursion, what you do, you basically, we're going to define fib recursive. So you have an input number which is going to be n. This is going to be the number that we're trying to find the list like up to. So if we're trying to find the say the 10th Fibonacci number, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're trying to find 55. We say 55 is equal to 34 plus 21, but we don't know what they are. We just know they're the previous elements. So what we say is, so we're going to say we're going to say return fib recursive of n minus 1 plus fib recursive of n is 2. So what this will do is it'll take your number and it'll return the same function called on the previous number plus the number before it. So for this it'll return this number plus this number, which this one will return this number plus this number, and this one will return this number plus this number. So you can see this gets really complicated really quick, but a computer can handle this. So what this is going to do is basically just branch out into a huge list of things it's summing up, and then in the end it'll cancel all down and hopefully return 55. Now you might spot that this is actually just going to loop forever. There's no end point. So what we need to add in here, we need to add some known values. So at the very bottom of our Fibonacci sequence, we know if n is equal to 0, then we want to return we want to return a 0, because that's the 0th term. Elif n is equal to 1, we want to return a 1. And now we want to do else, and then we want to do our step right here. So this isn't always going to be called. So once we get to the end of this, we want to if we say print and fib recursive, and we're going to say the third element for now. So if I run this, this is going to also print out the Fibonacci sequence down here so we can see it out. But you see the third element, it says is 2. The third element obviously is 0, 1, 2, 3, so it gets it right. It's actually found 2. So if I up this now to say 5, we would expect that we're going to get a 5. 0, 0, 1, 2, 3, 4, 5. So we would expect a 5 right now. And you can see we do actually get a 5. Now, if I want to print out the 10th, we get 55. So you see this is definitely working. So what I'm going to do now is just try and talk through it a little bit more. So if I come back to small numbers, so we say 3. Now, what 3 does, 3 goes in here and it says n is, so 3 is now n. Now 3 is not equal to 0, 3 is not equal to 1. So it says return fib recursive of 2, because that is n minus 1. So fib recursive of 2. So I want to do all this as a comment just to keep track of what we're doing. So fib recursive 3 is equal to fib recursive 2 plus fib recursive 1. Now hopefully you see this. The third number is the same as the second plus the first, so that's how the Fibonacci sequence works. Now we're going to look at what happens when you put each of these in. So that's going to be what happens the first time this function's called. Now what it's going to do is it's going to say fib recursive 2, because it's going to call this function right here. It's going to say fib recursive 2 is equal to, well, 2 is not equal to 0, 2 is not equal to 1, so it's going to have to call this section again. And it says, I'm just going to copy paste this because I'm sick of typing it. So it says fib recursive 2 is equal to fib recursive 1 plus fib recursive 0. Okay, so there's the next line done. Now the next line is going to be, it's going to call this one right here. This might not be the order of the computers, actually. I think the computer will probably do this one, but we're going to do this one. Don't worry about it, it doesn't matter. So fib recursive 1 has now been called, and it's going to say fib recursive 1 is equal to, now when 1 goes in here, it says n is not equal to So 1 is not equal to 0, but 1 is equal to 1, so it's going to return a 1. So this is just simply going to return 1. It's not going to return all these other functions. Now, that's the end of this. So then it's going to call these two right here that have been found. So it's going to say fib recursive 1 again, and now it's going to call this, so it will go solve it again, but you know this is going to come out as 1 again, the exact same, because obviously 1 is equal to 1 right here. So there's this part solved. Now, next line, you might already know what this is going to be. So fib recursive 0 is equal to, now 0 is equal to 0, so it's going to return a 0. So we get 0 right here. Now, once we've got these three, so we solved this, we solved this, we solved this, we solved this. Once we've got all these answers, what we do is we backtrack through and put all these answers in. So fib recursive 0 is equal to 0, fib recursive 1 is equal to 1. So fib recursive 2 is 1 plus 0, which is just 1. So now we have fib recursive 2 and 1. We can start putting the answers into this line. So fib recursive 1 is 1 and fib recursive 2 is also 1, which makes fib recursive 3 equal to 1 plus 1, which is 2. So hopefully that makes sense. And you see when we run fib recursive 3, you do actually get 2. So you can see that is what it's done. Now hopefully recursion makes a little bit more sense to you now. I'm going to quickly show like the downfalls of this. If I import time and I then say start time 1 is equal to time.time, and then I'm going to say start time 2 is equal to time.time, say recursion finished after seconds. Start time. Start time 1. So this isn't an exact comparison because obviously they're doing different things. This is just going to return the one number. I suppose actually I could make this return the one number. So if I print fib sequence minus 1, and I say if I change this to len of fib sequence and I say less than 10, I print out the 10. Do these both print the same number? So they do. So you can see we're getting the same number now. They are doing the same thing. They're just doing it in different ways. So this one creates a list of all the Fibonacci numbers and then prints out the last number, whereas this one will literally just print out the number. So if I now change, if I get rid of this main right here, which means that I can do that, and therefore get rid of this and just call this x. I'm also going to call this x, and then it means I can change x up here. So now x is 10, just check all this still works. So yeah, you see we get exactly the same again. Now what I'm going to do, I'm going to show how, so you can see for 10, the recursion is finishing lightning fast. It's actually not even registering time. Whereas the iterator does register a small time because it's got to compile that list. But you see if this goes up to 100 now, so we're stuck. Just by going up to 100 we're actually stuck. This is taking a very long time. This is because you saw when I typed out all this recursion stuff, as we got like through a line, we were generating 2 new lines, and then that line would generate 4 new lines, and it was like exponential growth sort of thing. you've just got an insane amount of computation to do. So you see when I cancel this, you're getting all these different lines that it's called, that it's trying to solve. So if I just drop this down to say 30, should be able to handle 30. So you see we get the exact same answer again, it's doing the same thing. This time recursion takes a hell of a lot longer than this list. This list is still taking like 0.004 seconds. 0004 seconds, sorry. Which, I'll go back to 10, was that taken before? So, actually it's taking 0 seconds now. There, so 0.0004, yeah. So, it's taking pretty much the exact same time again. Upping this to 30 makes the recursion, instead of being like instant, makes it take nearly half a second. Now if I make this 31, so it's one number bigger, you see recursion takes a whole 0.3 seconds bigger, because now I've just doubled the amount of branches. I've doubled the size of the thing I'm going through. That's the problem with recursion when you're doing it this sort of not very nice way. This isn't a very efficient way to do the Fibonacci sequence. Obviously there's better ways of doing this, as I've done down here. So yeah, this is the problem with recursion, and this is why in this lattice paths problem that I'm going to get to soon, even though this is 16 minutes in the video, this is why in the lattice paths problem I'm going to only be doing small lattices. I'm expecting this to fail or take a very long time for bigger ones. So with all that done, let's get started on lattice paths. So we're going to define main, and we're going to say, we're not going to define main, we're going to define, whatever, we'll just call it main. And this is going to be of a x point and a y point. Now my plan is, what we're going to do, if I go back to this thing right here, my plan is we're going to have xy point right here, so this is going to be 0, 0. It's going to say the number of ways for 0, 0 to go is, there's two different ways. The number of like possible paths in total is the same as the number of possible paths in total from here, plus the number of possible paths from here. And then it's going to say, right, the number of possible paths from this one right here is the same as the number of paths from here, plus the number of paths from here. You can see where we're going from this. We're going to just recurse through, and eventually when we get to here, we know there's 0 more paths. Or when we get to like here and here, I suppose we know there's just one more option. So that's what we're going to do. We're going to define these endpoints. You always need to define your endpoints first. So if x is equal to 1, if x is equal to 1, then we want to say return 1, because there's only one way for it to go. Elif y is equal to 1, we're going to return 1. Now I'm not certain I need this, so I'm just going to say elif, elif x is equal to 0, return, actually I'm pretty certain I don't need this, let's get rid of this. So else return main of x minus 1 y plus main of x y minus 1 y minus 1. So hopefully you see what I've done there. I've said that if you're at the end, like if you're at the point where we know there's only one option, then return 1. Else you want to return your current position minus 1. Is it minus 1 or plus 1? Yeah, minus 1. Else you want to return like the smaller matrix's value, so you want to like iterate through this. So basically doing what I said, where like if you're here, you're going to sum this one and this one to get the answer, and then these two will both sum their respective, like this one, and then this one will sum this and this, and so on, so on. So this is going to get really big really quick, same as how the Fibonacci sequence one did, but we're just going to call it anyway. We're going to call main, and we're going to say 5, 5 for now. I'm going to see if this runs. It might. I also want to print this. And I know the answer to 10, choose 5. So the answer we're looking for is 252. So if I save this and run, we get 70. So what have I done? What have I done wrong? What if I do 6, 6? Okay, so that was what I did wrong. So to do a 5x5 grid, you need to be calling in 6x6 for some reason. So yeah, so this works, and we're actually getting an answer. Now, if I import time and I say start time is equal to time, print what have I done wrong? Yeah, so 0 seconds for that. Now if I up this to 11 and 11, it's starting to take a little bit of time. So now we need 20 choose 10. So you see we've got 184,756, which is exactly the same. So we are getting the right answer. This is definitely working, which I'm pretty impressed with. I'm surprised I got this so quick. I thought I'd have problems. And it's still running really quick. I was actually expecting this to take a while already, so this might actually be able to go all the way up and give us our answer. So if I just up this to 2121, come on, don't take too. Yeah, let's cancel that. I just want to see roughly how long this is going to take. I'm going to call 16 and 16, so it's going to do a 15 by 15 grid. Wow, was it really going to take this long? Right, so let's have a look. So 11 by 11 takes less than 0.1 seconds. Now what about, say, 13 by 13? Right, so that takes, Jesus, that's good. That's a lot of time. So 11 by 11. Let's call these n. I say n equals 11. Right, so 0.06. Now if I up n to 12 and do a 12 by 12, that's just times it by 4, the amount of time it takes. Which I suppose makes sense because it's like you're adding double the arrays here and double the arrays here. So yeah, this is why I actually expected it to not work on a 20 by 20. I was right originally. So yeah, so I expect the next one's going to be taking like 0.9 seconds, which it does. So yeah, 13 takes 0.9 seconds or so. If I go to 14, this is going to take about 4 seconds. Yeah, so 3.6. Now 15 will take about, it would take about 16, maybe a bit less, about 14 seconds I would expect. 13, something like that. Yeah, so 14 seconds. Now, so we're doing a 14 by 14 there. We need to be doing a 20 by 20. So we've got like 6 more steps to do. So 6 more lots of times by 4. So we needed like 14 times by 4, 6 times. So to the power 6. So the power 6. And whatever the answer to that is how long this is going to take to run. So if I just drop this down to 10, just so it'll run instant, and then I print that right there. This will tell us how long it should run. So it's going to take that many seconds, which if I bracket the whole thing, and then I divide by 60. Oops. So 955 minutes, and if I divide by 1600, tell you how many hours. So about 16 hours to run. Assuming that I actually tried to run this for a 20 by 20, but it would give you the right answer. So it's going to be the end of this video. As I expected, I'm not going to be able to do this for a 20 by 20. There's probably a better way of doing this programmatically rather than just having to use the combinatorics approach that I've used. But yeah, figured I'd show what recursion is, how you use it, and I find it quite interesting, recursion. There's quite a lot of useful stuff you can do with it, with particular bits of code and things. It's quite an easy way to brute force a lot of answers. Like you can see for this, it's actually really simple code to get an answer out of it. It's just insanely hard to scale it up, because of the fact we're doing this like 4 to the power 6 thing down here. The time it's actually taking is like going up so fast that yeah, it gets out of hand so fast. Doing anything above like a 10 by 10 or whatever is pretty unrealistic. So yeah, that's it for this video. Hopefully you enjoyed it. Leave a like, subscribe, comment, whatever you want to do. If you're not sure of the combinatorics approach, look it up. There'll be a lot of information on that. It's basically like just a mathematical formula for solving problems very similar to this. But yeah, that's about it. So thanks for watching, and I'll see you in the next video. Hopefully it'll be not too long after this one. I'll probably make it tomorrow, so problem 16 probably coming out the day after this one. But yeah, thanks for watching. I'll see you in the next video.